Well, a warm welcome. Thank you for being here. Go ahead and get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we're going to finish off the Implicit Differentiation Summer Series. We're introducing the summer, welcoming the summer, launching you into the summer with a little bit of implicit differentiation practice. So go ahead and check out the first and second problem from this summer series if you haven't already seen those. Give them a try. The first one's a bit of a doozy, man. I'm not going to lie. So here we have yet another implicit differentiation problem. I'll go ahead and give you some space to look at the questions. They're kind of, sorry. Maybe I'll just sort of scroll through them so you can see. Part A, Part B, Part C, in all its glory. Go ahead and pause the video. Give yourself, 10 to 12 minutes to work on this. If you don't finish it in the 10 to 12 minutes, you should never feel bad. You should focus on doing things accurately. That's really what's more important. I'd rather you take 10 minutes and only get part A correct than take 10 minutes, do parts A, B, and C, and parts B and C are way off and A is correct. Then it's well, you're rushing. You don't want to rush through it until you have the accuracy down. Partially my best advice with getting good at mathematics. You want the accuracy to be great, and then you can work on the speed. That's most skills, really. When you practice a guitar, when I was practicing electric guitar in high school, I would want to do the crazy fast shredding and sweep arpeggios and really cool metal tricks and stuff. But really, the best warm-up for all of that was to do these sort of patterns very nice and slowly, and then repeat it, quicker and quicker, assuming that I didn't make any mistakes. It's kind of how you should approach getting better at problem solving in mathematics. Okay, without further ado, got a little intro blab there. Let's get started with the problem and come back and check how we do it here. So find dy dx. Sometimes on the AP exam, they'll say show that dy dx equals, and then kind of give you the derivative so that you can have a reference, but you still have to do the derivative in either case. So we're going to take a derivative of both sides, ddx of that side, ddx of that side. And remember, we have to use the chain rule here. So we're going to have 2y, but we have to multiply by dy dx. And then on the other side, 2 just goes to 0, but we do have a product here. So how do we do the product rule? Take a derivative of the first thing, leave the second thing alone. You can just place it there. Plus, we're going to leave the first thing alone, just place it there, and multiply that by the derivative of the second thing. So here we have 1 times y plus x times dy dx. Did I go too fast? Go ahead and rewatch that if that was way too fast for you. Now, because the plus distributes and there's only plus inside, it really doesn't do much. We can just call this y plus x dy dx. And this equals 2y dy dx. So what we're going to have to do is get all the dy dx stuff on one side. It doesn't really matter what side you pick. I guess I'll just sort of move this whole thing over. So we're going to have 2y, but we're also subtracting an x. And what I'm doing in one step here is I'm factoring out the dy dx, because everything on the left will have dy dx. So what's left, the pieces are 2y and a negative x. And this equals to y, which of course means that dy dx is y over 2y minus x. Pretty easy, straightforward. We got to use the product rule and then kind of isolate the variable, but nothing that basic algebra doesn't accomplish, right? Okay, let's take a look at part B. Find all points xy on the curve. They have to be on the curve. Remember, that's the caveat with implicit differentiation problems. Got to make sure that your derivative solutions, which are like theoretical solutions, actually work on the curve. We want the tangent line to have a slope of 1/2, the line that's tangent to the curve. So what does it basically tell us? This tells us that dy dx needs to be equals to 1 over 2 1/2. And we have the expression for it. That means that y over 2y minus x needs to be equal to 1 over 2. And this is simply a proportion. So you can cross multiply, right? That's an algebra skill that we use. So we need 2y minus x equal to 0. Okay, I see where this is going. So if we subtract 2y from both sides, then we end up getting negative x equals 0, which basically just means that x would be equal to 0. Now, if x equals to 0, we need the point on the curve, though. So we need to use x equals 0. If x equals 0, plug that into the original curve, and we have y squared equals 2 plus 0 times y. Oh, this is interesting. So y squared equals 2, which means we get 2 points here. We get that y equals square root of 2 and y equals negative square root of 2 is a solution. So therefore, we're going to have 2 points. They want us to find the points, not the equation of the tangent line. They just want to know what points have a tangent line with a slope of 1/2. So we're going to have 2 points here. We're going to have x equals 0 and y equals negative rad 2, and x equals 0, y equals positive rad 2. Those are the 2 points that are on the curve because we plugged in this x equals 0 result into the original curve equation. And so that gives us, happens to give us more than one y value, which is okay. That could happen. This is not necessarily a function, so an x value could be associated to 2 or more y values on a curve like this. All right, let's look at part C. Show that there are no points xy on the curve where the line tangent to the curve is horizontal. Okay, let's take a look at that. This is actually pretty easy. Horizontal, we saw this in a previous example from the summer series. Horizontal, and you should know this just from, being a young whippersnapper who is paying attention in calculus, dy dx, or the slope, is equal to 0. And since we have an expression for dy dx, that means this equals to 0. And this is only true when y equals to 0, the numerator of a fraction being 0, while simultaneously making sure that 2y minus x does not equal 0. And since y would equal 0 there, that means that negative x does not equal 0, or in other words, that x does not equal 0. So those are some conditions, some limitations. We need y to equal 0, but x cannot also be 0. Let's see what happens. Since we need to show that this is not possible, they're saying there are no points which do this. I'm guessing that when we check on the curve, this is going to be an equation that doesn't have any solutions for it. So 0 squared, that's y squared, equals 2 plus x times 0. Yeah, this is not looking good. 0 equals 2 plus 0. 0 equals 2. Well, that's just not true. So we can say since no solution exists, y cannot equal 0. So dy dx cannot equal 0. And if dy dx cannot equal 0, that means the curve is never flat/horizontal, because the slope of 0 would mean that it is horizontal or flat. So, a quick one indeed. I hope that only took you 10 minutes. Really, some of these problems are about interpreting the question and finding out what to do with this dy dx expression, which can look a little bit more hefty than this, to be honest. This isn't too bad to deal with. But when we say that the slope is equal to some value, which is a fraction, you just have to treat this like an algebra situation. You set this equal to a fraction, And then it's a little bit tricky to figure out, oh, you actually have to try to solve for x and y there. But if you realize that you have to find points x and y, I think it should be clear that you're like looking for x and y. Whichever one you can solve first is best. Okay, I think that's enough blab out of me. Hope you enjoyed the summer series and brushed up a bit on your implicit differentiation. There are some tougher problems, so I think I'm going to throw in a bonus video, which didn't come from problems that I wrote. You might remember if you watched the first video that this came from, these 3 problems just came from like practice that I wrote for a student to prepare for a test that was going to focus on implicit differentiation. But I do really want to challenge you a little bit more to the level of the AP exam. So I think to officially bring in the day before summer, the next video will be covering just that. I'll see you guys next time.